Problem 1.11 is a generalization of example 1.2. We covered this quite a while back. If you do not remember it, I would recommend you go watch that video first. It covers basically dropping a rock off of a cliff and taking a continuous series of photographs as it falls and analyzing the probability of where the rock would be if we randomly selected a given photograph from sort of our infinite continuous stack of photos. So in 1.11, we are given sort of a particle of mass m and energy E in a potential well V of x, sliding frictionally back and forth between the classical turning points A and B. And we are given a figure for this, thankfully. So we have sort of this physical realized potential well with our particle sort of just sliding back and forth. And since we're assuming that there's no friction or sort of air friction to sort of slow down or reduce the energy of our system, the mass effectively oscillates between these turning points A and B forever, or at least until we decide to insert energy into the system and stop it from sort of going up, or maybe change the turning points by making it go harder. So classically, the probability of finding a particle in the range dx, if we use the conclusion from example 1.2, is the ratio of the time it spends in this interval dx, which they call dt, divided by the total amount of time it takes for the particle to travel from A to B, which is big T. So we see here the probability of finding the particle in a range dx, if, for example, we took snapshots at random time t's, is equal to the fraction of the time t it takes to get from A to B that it spends in the interval dx. So we can see this here. The probability is dt over big T, where dt is the amount of time it spends in this interval dx, and big T is the total amount of time to go from A to B. And then we start using some algebraic manipulation here in order to sort of get this expression in terms of x. Since we have, in fact, a probability distribution in terms of x, we want that. So what we do here is we multiply the numerator by dx over dx, move the denominator of the dx sort of multiplication chain into dt, and this gives us the inverse of velocity, so the velocity moves down, and now we sort of get 1 over v of x times t times dx, and t here is just the total time, so we express this as the integral from 0 to the total time dt, which is also coincidentally equal to the integral from A to B of 1 over v of x dx, because dt is equal to dx over v of x, and in position space we go from A to B, so as a result of that our integral bounds go from 0 to big T to A to B, and therefore if we cancel out the dx's on both sides, we get rho of x is equivalent to 1 divided by v of x times big T in position space. Now, the first part of this problem, now that we're done with this very meaty introduction, is to use conservation of energy to express our velocity v of x in terms of the energy and the potential E and big V of x. So let's start that right away. And, well, we know that we're looking at sort of a classical analog of a quantum system. So in any sort of classical system like this, what we have is we have the energy of our system is equal to the kinetic energy of our mass, which is 1/2 mv squared, added with whatever potential our system has, big V of x. And this is generally the way we approach any sort of generic classical system, is that we have some particle that's moving, so it therefore has kinetic energy, and then everything else, including gravitational, electrical, etc., is all contained within our potential energy, big V of x. So now it is as simple as just isolating this expression in terms of V. So we know that 1/2 mv squared is equal to the total energy subtracted by the potential, E minus V. We do some moving around and we get that V is equal to the square root of 2 divided by the mass of the particle times the energy minus the potential. And this is our answer to part A. In part B, we are asked to find the probability distribution rho of x for a simple harmonic oscillator where v of x is equal to kx squared over 2. We are then asked to plot rho of x, and we want to, after that, check that it is correctly normalized. So, first things first, we are treating rho of x as a simple harmonic oscillator. Now, the fact that the potential v of x is equal to kx squared over 2 implies that our harmonic oscillator is centered about x equals 0, because the location where there is 0 potential is evidently x equals 0 from this expression here for v of x, and that implies that sort of our oscillator has to be centered around that point. And since we are dealing with a simple harmonic oscillator with no crazy offsets or any other weird conditions, because of that, the turning points are actually A and B have to be equal to each other. So necessarily, because of the fact that v of x equals 0 at x equals 0, A has to equal B. And that instantly tells us some very convenient things. First off, we know that v is equal to 1/2 kx squared. This is given to us. However, finally, the other thing we know is E, because E is just the total energy of the system, which implies that it would equal the maximum potential energy of our system. And since our turning points occur at A equal B, we can say that E is just equal to 1/2 k A squared, where sort of at the turning point, the potential energy is at its maximum and kinetic energy is at its minimum of just 0. So we can instantly start by writing out the velocity of our particle in terms of x and a instead of e and v. So we know that, let's just sort of copy this over. We know that v is equal to this. And we can say that this is in fact equal to the square root of 2 over m. And we're actually going to multiply 1/2 k, because that distributes it out, multiplied by a squared subtracted by x squared. And from here, we can sort of do some more simplification, and we can say that this is equal to, and the 2's cancel out, so this is square root of k over m. And I'm actually going to move the 8 out here for now. So this is going to become 1 minus x over a squared. So this is our sort of, well, let's try to make that a little bit nicer. All right, there we go. And then clean up a little bit here, make our expression a little bit more readable. So our expression for the velocity is apparently a times the square root of k over m times this expression of 1 minus x over a squared. And we can plug this back into our probability density because we know the problem gives us sort of this expression where we know that rho of x is equal to 1 over v of x times the total time. So we can plug this in, and we get that rho of x is in fact equal to 1 over t times a, and then we're going to flip everything over, so it's going to become square root of k over m, becomes square root of m over k because it appears in the denominator, and then multiplied by 1 over the square root of 1 minus x over a squared. And now we have to sort of verify that this is in fact normalized. So what does that mean? Well, if we integrate rho of x dx from negative a to a, we apparently require this to equal 1 because rho of x sort of defines our total probability, and x bounds from negative a to a because those are our turning points. And since it is a probability, sort of we cannot have any probability that surpasses or is underneath 100%. So adding all of our individual probabilities together must give us 1. So necessarily we require that the integral of this expression here sort of equates to 1. And this does give us a few problems, because we have a few values here that we can't seem to get rid of. They are apparently constants. For one, we have t. We have this big T value that we don't know what to do with. We have this square root of m over k that we don't know what to do with. And then hopefully integrating 1 over the square root of 1 minus x over a squared does cancel out the a term here, but we will see. So let's sort of write this out for now. So this is going to be, and I'm actually going to simplify this a little bit. We can carry out, since everything here is a constant, we can move it out of our integral. And then we multiply by the integral from negative a to a. Whoops, a little bit messy there. Negative a to a of our expression here, which is 1 over the square root of 1 minus x over a squared dx. And this is evidently supposed to equal 1. So since this is a physics course and not a math course, I will not be doing this. I feel like that's just kind of a waste of time. So instead, I'm just going to plug this into an integral calculator, and the answer for this specific integral ends up being pi times a. So this equals 1 over t times a times square root of m over k times pi times a. And this has to equal 1. So thankfully, the a does in fact cancel out. But that still leaves us with a bit of a dilemma, because we have these constants t, m, and k that we don't really know what to do with. So we in fact can do things with this, and the hint is that we have to take into account the fact that we're dealing with a simple harmonic oscillator. So let's sort of start doing some simplifications here, because there are certain properties of every sort of simple harmonic oscillator that we can use to sort of simplify these values. And primarily, the first thing, hopefully, that you recognize is that the square root of m over k is just the inverse of the angular frequency. Because we know that, so let's do this in a different color. One thing that we can say right away is that the square root of m over k for a simple harmonic oscillator is equivalent to 1 over omega, where omega is sort of the angular frequency of our simple harmonic oscillator. This is gone over in very high depth in early physics when you just start studying simple harmonic oscillators. So if you're not familiar with this, I heavily suggest you go back and review sort of vibrations and whatnot back in classical mechanics. Second, another thing we know is that we can actually link our angular frequency to the period of a simple harmonic oscillator. So we can say that omega is in fact equal to 2 pi divided by the period, which we will denote as tau. And additionally, t, big T, is the time it takes for our particle to go from one turning point to the other. So logically, in a simple harmonic oscillator, that is exactly 1/2 of the period. So we also know that big T is in fact equal to half of the period tau. And this evidently, if we plug in, will actually resolve everything, because if we sort this, then this becomes sort of 1 over, and then t becomes 1/2 tau. And then we're multiplying by 1 over omega, which becomes 1 over 2 pi over tau. And then finally, we're multiplying by pi. So evidently, there are a few cancellations that happen here. First off, tau cancels with tau, 2 cancels with 2, and then finally pi cancels with pi, and this does, in fact, equal 1. So therefore, rho of x is, in fact, normalized. Finally, the final thing that we sort of want to do here is we want to take this function, rho of x, which is this crazy thing right here, and we want to graph it. And once again, this is not a math class, this is a physics class, so we can simply just plug this into Desmos, or we can plug in, because this is a constant. Everything right here is a constant, so we can just sort of ignore this, which gives us the remainder, which is this. And if we just sort of treat a as a constant and ignore it entirely, the resulting graph that we get on Desmos looks something like this, where this is basically our probability density. So this is position, and this is our probability, rho of x. So we see that the particle has a very high probability of sort of being near the turning points of our oscillator, because at these points, these points are where sort of the kinetic energy becomes zero. So because of that, the particle slows down and spends a lot more time near the edges here compared to near sort of the origin, where there is no kinetic, or where there's no potential energy, because here kinetic energy is a maximum. So the particle sort of zooms back and forth and spends very little time in the middle. So this graph does in fact make sense, and since rho of x is normalized, we can sort of confidently assume that our calculations here are in fact correct. Part C is a relatively trivial part of this problem. Granted, mathematically it can be a little bit complicated to do, but physics-wise this is very simple because it is literally a plug and chug. So for part C, we want to find, for the classical oscillator mentioned in part B, we want to find the expectation values of x, x squared, and the resulting standard deviation. We have done this many times before, and we know that the formula for expectation value of anything is just equal to the integral negative a to a of x multiplied by rho of x. And we already have rho of x all the way over here. So we're going to put that sort of right here. And once again, this is a physics course, not a math course, so I will not be doing these integrals fully because they are quite painful and will take a good amount of time to do and don't really contribute to the actual physics of the problem. So we're just going to plug this into a calculator, and this does in fact just give us 0. And quantitatively, hopefully this does make sense. Our particle is sort of in a standard harmonic oscillator that is centered around 0, so logically it would spend an equal amount of time to the left of our equilibrium point and also an equal amount of time to the right of our equilibrium point. So as a result, we expect the expectation value of x to be 0. Second, the expectation value of x squared. This is once again another plug and chug, where we do the integral from negative a to a of x squared times rho of x dx instead of just x times rho of x dx. And once again, plugging into our integral calculator, this will give us a squared over 2. And then finally, to find the standard deviation of x, well, we know that the formula for this is just the square root of the expectation value of x squared, subtracted by the expectation value of x itself squared. And since this is just 0, we know that this is just equal to a over root 2. So these are our 3 answers.